Chapter 6.6, Solving Exponential and Logarithmic Equations. We're putting both kinds together, exponential and logs, and we're putting them together because they are inverses. They undo each other. Add and subtract go together, multiply, divide, radical and exponent, and then exponential and log. And remember, the difference between an exponent problem and an exponential problem is where the variable is. Exponent, it's a variable base with an exponent top. Exponential is a number base with an exponential, or a variable exponent. So we're going to start with exponential equations, solving those, and it will tie into logs because they work with each other. This first thing we need to know is about the property of equality for exponential equations, which says, the important part right here, b to the x equals b to the y if and only if x equals y. And what that tells us is that if we have the same base, we can just drop the bases away and set the exponents equal to each other. Because whatever that base number is, whatever its exponent is, it will only be equal to the same exponent. 2 squared is only equal to 2 squared. It's not equal to 2 to the third. So they have to be equal. So you can drop the bases and just set the exponents equal to each other. So let's give it a shot. Solve each equation. What we need to do is get the base to be the same, and then we can drop the base. Well, I have 100 and I have a 1/10. Those are not the same. But I can make them be the same because they're in some way related to 10. I could rewrite 100 as 10 squared to the x, and I can rewrite 1/10 as 10 to the negative 1 to the x minus 3. Now I just combine the exponents, because an exponent to an exponent, use that property, I multiply. So that's 10 to the 2x equals 10 to the negative x plus 3. The negative goes to both. Since the base is the same, drop the base. 2x equals negative x plus 3. Then solve for x. Add the x over. 3x equals 3. Divide by 3. X equals 1. And that's how it goes. Let's look at b. 2 to the x equals 7. There is not a way to write 7 as a base of 2. But remember the opposites. If it was a multiply by 2 and I wanted to get rid of it, I'd divide. Since it's a base of 2 and I want to get rid of the base, I can just move it to the other side. Right? So I can do x equals log base 2 of 7. And then if I wanted to, I could type that in the calculator. And functions 2 of 7, 2.807. So x is about 2.807. Another way to look at that is we can raise both sides to log base 2, and log base 2 of 2 cancels itself out, leaves me with just the x part, and I've got log base 2 of 7. That's actually how this slide it over move works, is you're doing log base 2 to both sides, and then the log base 2 of 2 cancels itself out, and it leaves you with just the x part in the exponent, which drops down to be the base number. And so we have our answer there. Now, a word problem with exponentials. An important application of the exponential equations is Newton's law of cooling. You won't be required to memorize it, but you'll be required to use it. It's right here. Newton's law of cooling. It's got a lot of variables in it. They're all labeled. This law states that for a cooling substance with an initial temperature T sub 0, the temperature T after little t minutes can be modeled by T for temperature equals temperature 0, or the starting temperature, minus T sub R times e to the negative little rt plus T sub R. So where T sub R is the surrounding temperature and R is the cooling rate of the substance. So we got to know what everything is. So this guy's the surround. This little thing's the rate. This thing is time in minutes. This is still the surround. This is the start. And after all of that stuff happens, this is your temperature after time. So, you are cooking a licha, an Ethiopian stew. When you take it off the stove, its temperature is 212 degrees Fahrenheit. That is T sub 0. The room temperature is 70 degrees Fahrenheit. That's T sub R, the surrounding room. And the cooling rate of the stew is R equals 0.046. How long will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? That's big T. All we have to do is plug them in. So if we've got T equals T sub 0 minus T sub R times e to the negative RT plus T sub R. The question asks us how long. So we're going to be looking for T is approximately. That's what we're going to fill in. So let's plug in all of the blanks. T sub 0 is 212. So that's 212. The surrounding room temperature is 70. The rate is 0.046 T plus the surrounding temperature is 212. And it's going to equal, when does it equal 100? Okay. So let's start stepping that bad boy down. All right, first of all, oh wait, surrounding is not 212. Here we go. 70. That was the starting temperature. All right, first of all, what I can do is I can get rid of the 70. That leaves me 30 equals, and I can also do this subtraction here. Let's see, 212 minus 70. Let's borrow 12. Actually, I don't need to borrow. Lie. 2 minus 0 is 2. Then 21 minus 7 is going to be 14. So that's 142 e to the negative 0.046 t. Okay, a little closer there. Let's divide by 142. Now those are both evens, so I could shrink that down to 15 divided by 71 equals e to the negative 0.046 t. Okay, erase these guys and draw me a little line here to work from on the next side. Then I need to get rid of the e base because I got to get the t out of the exponent spot. To get rid of a base of e, I use the natural log. That's the opposite. Whatever the base is, its log base of that is the opposite undo. So ln of 15 divided by 71 equals negative 0.046 t. Negative 0.046. And t, well, wiggles, we need approximately. All right, go over here. Close, close. Functions, ln 15 divided by 71 divided by negative 0.046. So 33, heck, we're in minutes, let's just round it up. 34 minutes it will need to cool in order to be at 100 degrees ready to eat. That's how it takes. So that's kind of a monster. There's a lot to do. Okay, main thing is identify the variable you have to isolate. Everybody else has got to move to the other side. So start on the outside, work your way in. Move your 70, do your divide away, then get rid of your base by doing a log of that. So if it's an e, you're going to do log of base e, which is an ln, the natural log. If it wasn't base e, if it was 142 times 2 to the negative 0.046 t, you do log base 2 to both sides. But it was an e, so we did ln. And that's how you work that. So when you get to that kind of problem in your homework, come back to this example and look at how they did it. Here's a couple right here. Give them a try. See how it goes. Come back. See what happens. Let's look at number 1. That's a highlighter. Need a pen. 2x equals 5. 5 can't become a 2. So I'm just going to log base 2 both sides. That goes away. X equals log base 2 of 5, which is approximately 2.322. And let's change colors to do number 2. 7 to the 9x. I'm just going to do the move over kind. 9x equals log base 7 of 15, because there's not a way to make a 15 a 7. Then divide by 9. X is approximately log base 7, 15 divided by 9. 155.0155 approximately. Very good. And let's try number 3 now. Ooh, lots of things to do. I'm going to add 7 first. So we got 4e to the negative 0.3x equals 20. Divide by 4. E to the negative 0.3x equals 5. I'm going to ln both sides. It gets rid of that. Negative 0.3x equals ln of 5. 0.3. Oops. So x is approximately. Okay, so we need the ln of 5 divided by negative 0.3. Negative 5.365. Boom. Okay. Now let's do that tough one. Okay. Let's work on that word problem. It's that same problem that we just did on the page previous. Okay. Or the previous slide. So I just have to bring that equation back over. So I'm just going to copy it. Get a little cheat. Paste. Okay, there's my equation that I need. How long would it take to cool a stew to 100 degrees when the room temperature is 75? So everything else stays the same. We want it to get to 100 degrees. It starts at 212, but the room's 75 degrees. What was that? 0.046. It's just going to follow the same pattern. Let's get rid of that 75. 25 equals, let's see, 212 minus 75. Now we got to borrow. 12 minus 5 is 7. 20 minus 7 is 13. 137. E to the negative 0.0462. Divide by 137. These are both odd, and they don't end in 5 each, so we're just going to leave it as 25 divided by 137. You could approximate here, but double approximating, you're approximating now and you're approximating later, it ends up losing decimal places. So I'm just going to leave it exactly correct for right now. We're going to ln both sides, which crosses that out. So the ln of 25 over 37 equals negative 0.0462. And we're going to divide by the negative 0.046. So t is approximately, we'll round it into whole minute here, ln 25 divided by 137, that's supposed to be a 1. And over, close, divide, negative 0.046. So, about 9 minutes. If we round to the nearest minute. 8.5 minutes, really. Probably a better one, because you can do 8.5 minutes pretty easy. Okay? 8.5 or 9 minutes. No, they said 37 minutes. I missed something. Let's see. Did I do 212 minus 75? Okay, that one's good. Functions. ln 25 divided by 37 divided by negative 0.046. I must have typed it wrong. There we go. That's why we check our answers in the back and make sure. time is about 37. That's 2 sevens in a row. 37 minutes. That's what we need. There we go. Always check your answers in the back. Make sure you know what's going on as you're going. You can always plug it back in and double check. Now let's go on to solving logs. They're going to be like solving exponents. We're just going to use that property of them being inverses to undo logs. Plus we're going to use those log properties we looked at in the last section, where if they're multiplying together, you can separate them to add. If they're dividing, you can separate them into subtract. If it has an exponent, you can bring it out in front. You can also take it from the front, put it out in front. Okay. A preceding property implies that if you are given an equation x equals y, then you can exponentiate each side to obtain an equation of the form b to the x equals b to the y. This technique is useful in solving logarithm equations. So, if bx and y are positive real numbers and b is not 1, log base b of x equals log base b of y, if and only if x equals y. So we can drop the log base. If it's the same log base, left side, right side, we can drop the log base and just use the parts on the inside. So, let's solve. Look at A first. The ln of 4x minus 7 equals the ln of x plus 5. These are the same log base, so we can just drop them. 4x minus 7 equals x plus 5 minus x. 3x minus 7 equals 5. Add 7. 3x equals 12. Divide by 3. X equals 4. Let's look at B. Log base 2 of 5x minus 17 equals 3. Well, this time we don't have a log on both sides. But remember, like it said, if we raise to the same power, then it makes those sets equal to each other. So what we can do here to try to get these out of there is we can raise them to the same power. So what I'm going to do is I'm going to say log base 2 and 2 to the third. So 2 to the log base 2 cancels out. Leaves me with 5x minus 17. Now it's free from the exponent zone. And 2 to the third is 8. And then I just solve. Add 17. 5x equals 25. Divide by 5. X equals 5. Because the domain of a logarithmic function generally does not include all real numbers, be sure to check for extraneous solutions of logarithmic equations. You can do this algebraically or graphically. Okay, so if we graph something like the log of 2x plus the log, wrong log, the log of x minus 5 equals 2. When we graph something like that, it's going to come right through and give us one answer. Now, if I do it and I don't put equals 2 and I say equals y, it gives me a nice graph here that I can look at. It gets really close. Let's go back to home. It gets close to probably 5, but doesn't ever touch it. So if we get something that is less than 5, it's going to be an extraneous solution. We can also we can plug it back in and check and make sure that that works. So let's look at solving this one. Now, we have 2 logs on one side and none on the other. Even if we subtract it, then we're going to get in a weird place. So what we want to do is we want to cinch these up into one log. So if I go log, and then because it's a plus sign, I'm going to say 2x times x minus 5 equals 2. And this is log base 10, okay? So what we have is log of 2x squared minus 10x equals 2. Okay. Now what we can do to get rid of the log part is bring on a new base. Log base 10, 10 to the log base 10 drops out, gives us 2x squared minus 10x equals 10 squared. So 2x squared minus 10x equals 100. Move the 100. This is a quadratic, so we're going to set it equal to 0. So 2x squared minus 10x minus 100 equals 0. Now what I would do is I'd divide the 2 out of everybody. Make it x squared minus 5x minus 50 equals 0. And I need factors of 50 that subtract to be 5. Well, that would be 5 and 10. The 10 needs to be negative because it needs to be a negative 5. So that means x equals negative 5 and x equals positive 10 when we do opposite to get out. See how all that quadratic stuff we did back in the day always comes back to us. Now, if I look at my graph, negative 5 is not on the graph, but 10 would be. Okay, so that one's going to be out. This one's going to be good. And we can check it by plugging it in. So let's try. We need to get 2 whenever this happens. So let's do log of 2 times negative 5, close, plus log of negative 5 minus 5, close, close. See, it's undefined. Now, if we go back and put in the 10, we get a 2. 10 works, negative 5 doesn't. So watch for those extraneous solutions. Make sure you check them. Okay? Solve the equation. Check for extraneous solutions. They're telling you there might be some in there that don't work. Okay, a lot of times it's going to be whenever you get that squared in there, that's going to be your clue that you really should check. So give it a pause, try these, come back. Okay, here we go. Number 5, start with red. ln of 7x, oh, screw that. Not even going to do that. Look at this. They're both equal to ln. There's nothing extra on them. Drop the ln's. 7x minus 4 is 2x plus 11. Minus the 2x. 5x minus 4 equals 11. Add 4. 5x equals 15. Divide by 5. X is 3. Let's try number 6. Log base 2 of x minus 6 equals 5. I'm just going to scoot that over. That's just like raising it to a 2 and to a 2, right? So those drop. X minus 6 equals 2 to the 5th. So x minus 6 equals 32. Add 6. X equals 38. Only got one answer, so I doubt that it's extraneous, but I could plug it in the calculator and make sure that it works. Log base 2 of 38, what was it? Minus 6. And we got a 5, so we're good to go. Okay, let's look at 7 and 8. All right, I'll switch colors again. 7. Logs on the same side, so what I'm going to do is I'm going to combine them. Log base 5x times x minus 1 equals 2. I'm going to move the 10 over, so it becomes 5x squared as I multiply these in, minus 5x equals 10 squared. 5x squared minus 5x equals 100. Move the 100. 5x squared minus 5x minus 100 equals 0. I'm going to divide my 5 away. X squared minus x minus 20 equals 0. So we need factors of 20 that subtract to negative 1, and that would be 4 and minus 5. So x equals negative 4 or positive 5. Let's graph the original and see what doesn't belong. Log of 5x plus log x minus 1 equals y. That's at a 1, so it's got to be greater than 1. So negative 4 is out, just the 5. You always want to put the original equation in, because as you start simplifying things and things go away, you're not the same equation anymore. Let's look at number 8. Number 8, log base 4, x plus 12 plus log base 4 of x equals 3. Those log base 4s, I'm going to combine them. So number 8, log base 4 of x, too high, x plus 12 times x equals 3. Distribute that in, and I'm going to move this over. So x squared plus 12x equals 4 to the third. 4 times 4 is 16 times 4 should be 64. So x squared plus 12x equals 64. Move sides. X squared plus 12x minus 64 equals 0. And we just saw, let's see, 4 times 4 is 16. And then times 4. So that's the ones I'm going to use because that's a difference of 4. So we got 16 and 4. They need to subtract to positive 12, so that way. So x equals negative 16 or 4. Let's graph the original. So we got log base 4 of x plus 12 and plus log base 4 of x. And it has to be greater than 0. So 16, negative 16 is out. Just the 4 is the one that works. Solving exponential and logarithmic inequalities. So all we're doing here is we're changing out the value, the equal sign for an unequal sign. And the only thing you have to remember different about inequalities versus equalities is if you multiply or divide both sides by a negative, you got to flip the sign. Okay? And that's all the difference is. Other than that, it's just like doing an equal sign. Okay? So exponential property still works. B to the x greater than b to the y if and only if x is greater than y. Same with less than. Same with logs. Okay? All of the same properties still happen. So if we're going to solve this, I'm going to move the base, which is saying log base 3 of 3 to the x, log base 3 of 20. But the quick move is just to slide it. Those go. X is less than or equal to log base 3 of 20. And whatever that is as a, I don't know how to do a squiggly unequal sign, but whatever that is as a decimal, you just type it in and find it. Solve log x less than or equal to 2. Well, that's base 10. Slide it over. X is less than or equal to 10 squared. So x is less than or equal to, is that what I did over here? Yeah. 10 squared is 100. Wow. Boom. Try some. Pause it, try it, come back. Okay, here we go. Number 9, e to the x. Got to move that over, which means we're going to ln both sides. Ln of e cancels out, leaves me x equals less than or equal to ln of 2. You can get the decimal if you need to. Okay, you can get the decimal if you need to. Now, this one, move that over. 2x minus 6 greater than log base 10 of 3. So I can just say log of 3. Add the 6. 2x greater than log 3 plus 6. Divide by 2. Whole thing by 2. X greater than. We can do the decimal on this one. That'll be fun. We're doing log 3 plus 6 divided by 2. 3.239. There we go. Checked it, and it is correct. I'm going to erase, give me some room for 11 and 12, just in case they're weird. All right, so 11. I would move the 9 first. Log of x less than 36. That's base 10. Move it over. X is less than 10 to the 36th. Now let's look. If we do that, log of x plus 9. Let's see. Where'd it go? Log of x, close, plus 9. Okay. Notice that it goes here at 0. It gets really close to 0, but doesn't get any lower than 0. So that's a limit. So we have to check those. Remember that logs are going to have limits to them. They don't go a certain amount left or right. There's a stopping point. There's an asymptote. So we actually need to add in, it also has to be bigger than 0. It doesn't touch 0, but it's anything that's bigger than 0, and it can't get any bigger than 10 to the 36th, which is pretty huge. That's a 1 with 36 zeros on it. So, big deal. Okay. Now, 12, I'd add the 1 to ln of x is greater than 5. I'd divide the 2. ln of x is greater than or equal to 5 over 2. And then I'd e both sides. X is greater than or equal to e to the 5 halves. And let's see what e to the 5 halves is. Nope, not funks. E to the 5 divided by 2. 12.182. So x is greater than or equal to 12.182. That's you got exact here, and you got approximately there. And that's just doing inequalities. It's just like equal sign. The only thing you have to remember